In the previous lecture, we discussed more about how to make the bandwidth of the quarter wave transformer better by means of having a maximally flat response of gamma as a function of frequency or theta, and therein we talked about the concept of repeated minimas or repeated roots and developed the concept of what is called as the binomial or the Butterworth matching transformer. Now, it very rarely happens in real life that the loads you see that a transmission line has to feed, those loads will be purely resistive. It so happens that the loads may be complex, they may be inductive, they may be capacitive, they may be some combination of resistive and reactive. So let us say, for instance, let us say we have a bipolar transistor which is working at RF frequencies. Yes, there are transistors which work at very high frequencies also, and we shall discuss about these later. So the question is that if there is a RF input to the transistor, what would the signal see? So essentially you will have to look at the small signal model of this bipolar transistor. So let us quickly take a recap from our basic analog course and see what it would look like. So effectively it would look something like this. This is the resistance between the base and the emitter. So that is this beta times small re, which we call. Then there is a current source that is flowing. This is the base, this is the collector, and this is the emitter. So as you know, the collector base junction is reverse biased in a BJT amplifier. So there will definitely be some capacitance which is seen in the reverse bias because of the depletion region which is caused between the collector and the base. So this is called a CCB. So now if I am looking into this base, now let us say even the emitter is seeing AC ground. What will essentially happen is that the input impedance looking into the base of this transistor will be some combination of resistive and capacitive. So therefore the impedance of this device in general will be complex. But the question is for complex impedances. So if ZL is complex and Z0 is real. So if Z0 is real, it has to be real because the main transmission line that we want to use for carrying energy from the source to the load, it has to be a lossless line. So in that case, if we were to ask ourselves, if ZL is complex, what if we use a quarter wave transformer? If we are using a quarter wave transformer, Z1, that will be nothing but Z0 square by ZL. So Z0 is real, but ZL is complex. So that means even Z1 will be complex. So a transmission line or a quarter wave transmission line of characteristic impedance which is complex, that means that the line has to be lossy, which we don't want. So this is not at all desirable. So Now, there is one more way to look at it. That is even if you say that, okay, let us say I don't mind a lossy transformer. I'm willing to have some loss, no problem. But even then, can I use the QWT? Well, not really. Because if your ZL is some R plus JX, where let us say this JX is some J by omega C, or let us say this will be minus, where omega is the angular frequency. So therefore, even if you are able to match at one frequency, the moment omega changes, the matching network will fall flat. Therefore, one problem with complex loads is that they will have narrowband matching. Matching is possible with L and C components in the load only at a single frequency. Why? Because if the frequency changes, the impedance of those reactive components will also change. So thereby making the matching network pretty much useless. So this is another challenge. So in this particular lecture, we shall take one step into understanding what is the bare minimum things that we need to match a complex load to a lossless transmission line. So thereby, let us take an example. The best way to understand some concept is to take an example and then follow it. So suppose I tell you that I have a load impedance ZL that is 10 plus J10 ohms. So the moment I am saying this, I have to specify the frequency because the reactive component depends on frequency at F equals 1 gigahertz. And this load is to be connected to a line of impedance 50 ohms. Right? This is one way. This is the specification that is given to you. Now the point is, I have this line Z0 as 50 ohms and I have to connect the load ZL that is 10 plus J10 ohms. Once again, I have to introduce some kind of a black box over here with some question mark, which will sort of make the main line see that the impedance looking over here is still 50 ohms. Now, is that possible? Is that possible? Well, it is possible. And it is a technique that you have learned already in your basic waves course. And that is the concept of stubs. So a stub is a piece of transmission line that is terminated with either a short circuit or an open circuit. So, to understand how the stub works, let us look at this problem. So, let's first calculate the normalized impedance. That is small zl, which is capital ZL by Z0, which is 0.2 plus j 0.2. So the idea now is as follows. Since I am only making a recap of a stub, I shall show you one case. That is, suppose I have a load impedance over here. I have to now move away from the load towards the source until the point where the real part of either the impedance or the admittance becomes 1. That is, I have to start from here and keep moving towards the left or towards the source until I reach the point where the real part of the normalized impedance or the admittance essentially becomes 1. Now, what is admittance? Admittance is nothing but 1 by impedance. So admittance symbol is Y, impedance symbol is Z. So just to refresh some terms, the reciprocal of resistance is conductance. The reciprocal of reactance, which is a purely imaginary quantity, the reciprocal of reactance is called as susceptance. These are few terms that we are just brushing up. So now, if we have transformed to a point where the real part of the normalized impedance or admittance becomes 1, there we can connect a stub. If you are using normalized resistance, you can connect a series stub. If you are using normalized admittance, you can connect a parallel stub. So often what happens is, it is easier to work with parallel stubs. So therefore, let us look at the parallel stubs, and therefore let us look at admittance. So we calculated the normalized impedance small zl as 0.2 plus j 0.2. So therefore, I will now take my calculator and calculate the normalized admittance, which is just a reciprocal of this. So therefore, YL, which is 1 by ZL, that will be 2.5 minus j 2.5. So if this load now is having an admittance of 2.5 minus j 2.5, the normalized admittance, I am going to transform this And let us say I will reach a point, some point where the admittance sort of becomes, let's say y prime, that is 1 plus minus j something. The important thing is the real part has to be 1. And let us say the imaginary part is some jb. So 1 plus minus jb. So therefore, what I can do, I can connect a parallel stub, either open stub or short stub, that does not matter, such that the reactance offered by this. Now, as you know, a transmission line that is terminated using either open circuit or short circuit, that can never have any real impedance. Even if you move further away from it, it can only have imaginary impedance or admittance. So therefore, the susceptance of this line should be exactly the opposite of this susceptance, that is minus plus jb. So therefore, because these two are in parallel, the admittances will get added up. Therefore, the effective admittance, normalized admittance, will be 1 plus minus jb minus plus jb, that is equal to 1, which makes it matched. So let us look at this actually by working it out on the Smith chart. So I have a copy of the Smith chart with me. So I'm going to use this as an admittance chart. So in the admittance chart, there is not much difference, except that in the impedance chart, this was the short circuit, this was the open circuit. Now in the admittance chart, this becomes open circuit and this becomes short circuit. So let us try to see how we can do this. We have the normalized admittance, that is 2.5 minus j 2.5. So the 2.5 circle is somewhere over here, the conductive circle, and the minus j 2.5 is somewhere over here. So minus j 2.5 is between 2 and 3, somewhere over here, and 2.5 in the conductance is somewhere over here. So let us say, since this does not have a coordinate for 2.5, let's go for 2.4. So this is 2.4 and this is also 2.4. So this is the point. Which point is this? This is normalized admittance. So therefore, let us mark this using a scale connected to the center of the Smith chart. Right? So this is my normalized load admittance, or we will say YL. Now, what was the principle? The principle was we are going to start moving towards the load. I'm sorry, we are going to move away from the load towards the source. So therefore, we can draw a constant VSWR circle above this. The radius should be as much as YL from the center of the chart. And we have to now start moving clockwise, that is this way. Until which point? Until the real part of the admittance becomes 1. So if you are moving this way, the first point where it happens is this. Because as you can see, this is intersecting with the conductance equal to one circle. The real part 1 is over here. But there is one more solution possible where you can move all the way over here. This is another point where the real part becomes 1. Only thing is it is further away. So therefore, let us try to keep things simple. So therefore, this point is y prime. This point is y prime. So what is y prime from here? 1 minus j 1.8. So what we got from here, y prime is 1 minus j 1.8. This is what we have. So therefore, I need a stub which will give me normalized susceptance of required stub that will be exactly the opposite of this imaginary part, which is j 1.8. j 1.8. So let us say we have over here an open circuit stub. So that means I am at this point and I want the susceptance to be plus 1.8. So that means I have to move all the way from this point to this point, 1.8. So therefore, let us draw this. So from this open circuit point, you have to keep moving this way until you reach here. Now, from this approach, we have to find two things. The first thing is called ds, that is the distance of stub from the load. And the second thing is ls, or the length of the stub. So the distance of the stub from the load will be what distance? It will be the distance between yl and y prime. So therefore, let us again make a connection over here. So we are moving away from the load. So therefore, we should look at wavelengths towards generator. That is the outer circle. So here the reading is 0.284 lambda, and over here the reading is roughly about 0.318 lambda, roughly. So the ds will be a distance of these between these two. So therefore, ds is nothing but the difference between these two, that is 0.318 lambda minus 0.284 lambda, that is 0.034 lambda. This is ds. Now the ls, again going from open circuit point to this point, which is roughly about 0.17 lambda, and it's starting from 0. So therefore, ls is 0.17 lambda minus 0, which is 0.17 lambda. And once you know the lambda, you can quite easily find out what is the actual absolute dimensions. So this was a very quick recap of the stub matching technique. which you are already very familiar with. Now, the drawback of stub is that you need additional pieces of transmission lines, which may increase the requirement for more area. So the question therefore is, can any other approach be done? Can any other approach be done where the space consumed by the matching network is very, very minimal? So let us again say the same problem. The ZL is essentially 10 plus J10 ohms, and the line where it is to be matched has a characteristic impedance of 50 ohms. Well, the other technique which we are going to talk about starting now, this is called as matching using reactive elements. That means using inductor or capacitor. For the time being, the assumption is that ideal inductors and capacitors are available at high frequencies, and therefore we could use them. That is the assumption. So to discuss the theory, that is fine. So once again, let us calculate the normalized load impedance, which is ZL divided by Z0, which is 0.2 plus J 0.2. Right? Now, let us again use the Smith chart to do this. So, if I want to now mark the normalized load impedance point, that is 0.2 over here and 0.2 over here. So, this is the point. This I will say is small zl. Now, let us not forget the bigger picture. We wish to match this load to a line of 50 ohms. So therefore, in some sense, I have to move from this point to this point. Now, where is 50 ohm on the Smith chart? So 50 ohm corresponds to a normalized impedance of 1. So therefore, this is the point. This is the point where we have to reach. So now, we can look at this matching problem as more of a pathfinding approach. That is, in the Smith chart, what are the paths from which we can use to reach from ZL to Z0, which is the center of the Smith chart. Now, one way that you know is to have a transmission line. We draw the VSWR circle like what we drew over here. But the point is, if you move on the VSWR circle, we are always moving round and round. We will never reach the center. So therefore, we will just be making use of more and more length of transmission line, but we will never ever reach the center. So therefore, what can we do? This is the normalized load impedance, and the normalized 50 ohm point or the destination is Z equal to 1. So therefore, the question is, from this point 0.2 plus J 0.2 to this point, how can we move? Well, one intuitive way to think about it is to sort of say that, okay, somehow let me first make the real component of this into 1. Whatever happens to the imaginary component, we will see later. Something tells me that would be the way out. So therefore, now we are over here. Now, what are the ways we can move? We can move this way, on this line. So this is the inductive reactance circle. But what we are doing, if we are moving actually on the inductive reactance component, we are changing the resistance. That means we need to add some more resistance in the line, and that is we don't want, because we don't want the line to be lossy. Now another way to move is either upwards on this circle or downwards on this circle. Now what is this circle? This is called as a constant resistance circle of point. Now if I am moving up this way or down this way, the resistance is not changing. The resistance is still 0.2. What is changing is the inductance. Okay. Now one thing to remember is that this is not a VSWR circle. So moving up or moving down on these circles have no meaning on whether it is moving towards the load or away from the load. Okay, so that confusion, you can simply put it out of your head. So now the question is, let us say I am over here, which we are, and we start moving upwards. Even when we are moving upwards on the VSWR circle, we are coming here, and then we will come here. So it's not serving any point. This is which point? This is the open circuit point. And then again if we move, we are coming back to the same point on this circle. So it's not really working. Well, one thing is for sure. We have to move on this circle. We cannot move on the inductance circle. We have to move on the resistance circle. Because at least we don't want to add any more lossy elements. Right? So the point is, whether we are moving up or moving down, we don't know which is the right place to stop. Because what was our initial goal? We were trying to ensure that somehow if we can make the resistance component as 1. But the resistance component 1 is on this circle, and we can never ever reach this. Because the only place where we are meeting is the open circuit point, and that is of no use. Because it's not really meeting, it is just touching. So somehow we have to figure out a way to come to this circle. So now this circle is what we call as the R equal to 1 circle, or the constant resistance circle of value 1. Now, if I know that I can never reach the value of resistance 1, what is the next best thing? The next best thing is if we can reach the point where the conductance is 1. If we can reach the point where the conductance is 1 or the G is 1. So the question is, this is an impedance chart. That's what we are starting with. All coordinates are impedance coordinates. So if I now want to see the circle that corresponds to G is equal to 1 or the conductance equal to 1, what do? All I have to do is simply rotate the Smith chart by 180 degrees. And this becomes the admittance chart. So what is happening? Earlier, the R equal to 1 circle was here. Now it has moved here. So this becomes now the G equal to 1 circle. Well, this might sound very confusing because we are not used to rotating the Smith chart so easily. And that is what we don't want to do. So therefore, rather than rotating the Smith chart, what we can do is we can make a copy of this circle, R equal to 1 circle, and rotate it such that it comes here. This is the circle inscribed over here, which is a copy of this, and just rotated by 180 degree would become the G equal to 1 circle. So therefore, let's do this. So let's construct the circle quickly. So this is about 7.6. So is this, it's about 7.6. So the center would be somewhere close to 3.8. slight error, slight amount of error is fine, no issues. So therefore, we will call this as our G equal to 1 circle on the Smith chart. You can very easily verify this. Take any point and just take the reciprocal. You will get the real part as 1. So let us say I take this point, or let us say I take this point. So this is 0.1 minus J 0.3. So if I were to take the reciprocal of this, you see that the real part is 1. Okay. These coordinates are still impedance, but the circle is implicit. So any point on this circle will always have the conductance value as 1. So therefore now if I start from ZL and keep moving on this constant resistance circle, I will stop at this point. So I am going this way on this constant resistance circle of 0.2 and I am stopping over here. Right? So therefore, let me call this impedance as Z prime. And what is this impedance? 0.2 plus J 0.4. Now what have we done? We started from this point 0.2 plus J 0.2 and arrived at a point that is 0.2 plus J 0.4. So the resistance has not changed, but what has changed? The reactance has increased. The reactance has increased. So therefore it is like saying I have added a series inductance. So it's like saying if this is my load, if this is 0.2 plus J 0.2, I'm adding some impedance or inductance, and after this the impedance is becoming 0.2 plus J 0.4. So how much impedance am I, or how much inductance am I adding? The inductance that I am adding is J 0.4 minus J 0.2, that is J 0.2. This is the reactance. So therefore, we can now very easily calculate what is the value of the inductor actually. So normalized reactance is J 0.2. So therefore absolute reactance, we just need to multiply it with 50 ohms, that will be J 10 ohms. So that means this is equal to J 2 pi times frequency times L. Frequency is 1 gigahertz. We had already established that earlier. Frequency is 1 gigahertz. So therefore L will be what? 10 divided by 2 pi into 10 raised to 9. So that will be 1.59 nano Henry. This is the inductance that we need. Now, the problem is not solved completely. We are over here. Now what? Even if we have got G equal to 1, we are still at this point. Has that really done anything to ease our problems? Apparently not. Apparently not. So then what we have to do now is we have to make use of the fact that G is actually 1. So currently we are not able to make use of the 1 because we are still on impedance coordinates. So therefore, what we have to do now is we have to switch from impedance coordinates into admittance coordinates. And that's very simple. How will you do that on the Smith chart? You will do that on the Smith chart by connecting a line from the center to the impedance point and extending it diametrically. So therefore, what you need to do is from this point, just take the radius of this Z point and mark its equivalent on the other side. So that intersection is the admittance corresponding to that impedance point. So if this is Z prime, this will be Y prime, and Y prime is what? 1 by Z prime. So Y prime is 1 by Z prime. We can very easily mark that point out from the Smith chart, and that is 1 minus J2. 1 minus J2. 1 because of this circle and J2 over here. Minus because it is in the lower half. Now finally, we are over here. Now notice that we have just changed the coordinates. We have not added in anything. The Z prime impedance point has an admittance of Y prime. So we have just changed our frame of reference. We have not added anything. But by doing so, we have transformed from impedance coordinates into admittance coordinates. Now what we can do, we can very easily from this point move along this circle, which is the unit circle or the real component 1 circle, this way, and we can stop at the center. Lo and behold, there we are. So even if we are in the admittance coordinates, the center is one and the same whether the coordinates is impedance or admittance. But now, because we are in the admittance coordinate, we have to be a little careful. We are at this point. We are at the point where we had added that inductance. So at this point, this is that Z prime or Y prime. And what is happening is we are moving from Y prime to the point 1. So effectively, we are increasing the susceptance. Increasing susceptance means what? It means which component contributes to an increase in susceptance. Increase in reactance is a series inductor, but increase in susceptance is contributed by a shunt capacitor or a parallel capacitor. Increasing, so if you are on an R circle, going up means increasing of reactance, so therefore series inductor. If you are there on the R circle and you are going down, means you are decreasing the reactance, so therefore it would mean a series capacitor. But now we are on the admittance circles, we are on the conductance circles. So therefore conductance, admittance means increase decrease happens in parallel. In the impedance coordinates, increase decrease happens with series components, but in admittance coordinates, increase decrease happens in parallel configurations. So therefore, I am going up on the constant conductance circle. That means I am adding some component whose susceptance is positive. That can only happen if the component has negative reactance, and that is capacitor. So therefore we are adding a shunt capacitor. So the final point is 0, initial point is -2. So therefore we will say added susceptance, that is normalized, that is 0 minus j 0.2, which is j 0.2. This is susceptance. So therefore the absolute reactance will be 50 divided by this, that is 50 divided by j 0.2, which is equal to minus j, or 25 by j, sorry, not 0.2, this is j2, yeah, this is j2, y prime is j2, yeah. So sorry for the error. So absolute reactance will be 50 divided by j2, which is 25 by j, and capacitive reactance for that will be 1 by j 2 pi fc. So j and j get cancelled. Simply substitute the frequency of 1 gigahertz and you will get the capacitance value to be somewhere at about 6.37 picofarad. So now in the diagram, from z prime coming to 1, all we need to add is a shunt capacitance of 6.37 picofarad, and the impedance that you see over here would be exactly normalized to 1, and therefore the absolute impedance seen over here will now be 50 ohms. So now you will notice that this is not the only possible solution. This is not the only possible solution. There can be many number of solutions. Rather than going up from here, you could have come down over here, and then you could have switched. That would have meant a series capacitance followed by a parallel inductance. That is also possible. So one that we saw was, we have the load first, then series inductor, then shunt capacitor, and then we are seeing the matched impedance. This is the first that we can do. The second is what I explained, when you can first go down and then switch to the admittance. Then this would have been this load, then series capacitor followed by a shunt inductor, and then you are saying 50 ohms. Any other solutions are possible? Well, it is indeed possible if you start itself from the admittance and later go to the impedance. So that is, if you start with the admittance chart and later switch over to the impedance chart. In that case, the first component you will see will be in parallel. So therefore it will look something like this. If you are starting with admittance and moving down, you will get a shunt inductance followed by series capacitor, and then here it will be 50 ohms. And the last solution is, if you take admittance coordinate but you go up, that will be first a parallel capacitor followed by a series inductor, and here you will see 50 ohms. So therefore it is your responsibility to solve one problem in multiple ways, so as to ensure that you have possible solutions in all 4 configurations. This will be a very interesting exercise and I recommend that you do this. So in today's lecture, we started the discussion on how to match complex loads to a transmission line, and we saw essentially two ways. One is the approach that you have already learned, which is the approach of using stubs, and secondly, the approach of using lumped elements, that is inductors and capacitors, to do the matching and without using any additional stubs. Thank you.